A diagram showing the relationship between all three phases of a substance and the temperature and pressure in a closed system is called a phase diagram. The phase diagram for water is shown here. Note that the temperature is not to scale. The diagram consists of three curves. Click on the cursor in the areas between the curves, avoiding the area around the intersection. How many phases are there in each area? Answer: only one. Now move the cursor along each of the curves, holding down the mouse. Again, avoid the area around the intersection of the curves. How many phases are present at points along each curve? Answer: 2. Which phase equilibrium does each curve thus represent? Answer: right-hand curve, liquid vapor. Upper left-hand curve, solid liquid. Lower left-hand curve, solid vapor. The point of intersection of the curves is a unique point, called the triple point. Click on it to see the particles. How many phases are present at the triple point? Answer: all three: solid, liquid, and vapor. This is the only set of conditions. T equals 0.01 degrees Celsius. P equals 0.61 kilopascals, at which solid, ice, liquid, water, and vapor, water vapor, can all coexist at equilibrium in a closed system. The solid-liquid curve for water is unique in that it slopes to the left. The curve is said to have a negative gradient. This has some important consequences for ice skaters. Place the cursor on the solid-liquid line at a pressure equal to the atmospheric pressure, taken as 101 kilopascals. At what temperature are ice and water at equilibrium at this pressure? Read the value on the diagram. Answer: 0 degrees Celsius. What is this temperature usually called? Answer: the melting point of ice or the freezing point of water. The solid-liquid line is known as the melting point curve. Now move the cursor up the melting point curve, increasing the pressure. What happens to the temperature at which ice and water are in equilibrium as the pressure increases? Answer: the temperature drops. What effect does this have on the melting point of the ice? Answer: it will lower the melting point of ice. This decrease in melting point of ice with increasing pressure is linked to the fact that the volume of ice decreases as it melts. In other words, the volume of water in the liquid state is less than that in the solid state. Thus, an increase in pressure favors a change from the solid to the liquid state. Which is denser, ice or water? Answer: water. The phase diagram for carbon dioxide is essentially similar to that of water, but there are two differences to note. Firstly, the solid-liquid curve for carbon dioxide slopes to the right. What effect does increasing pressure therefore have on its melting point? Move the cursor up the solid-liquid line if you need help. Answer: as pressure increases, the melting point rises. What can you deduce about the volume of carbon dioxide in the solid and liquid states from this? Answer: the volume of carbon dioxide is higher in the liquid state than in the solid state. Secondly, the triple point is at a pressure higher than 101 kilopascal, 1 atmosphere. What change in state will solid carbon dioxide undergo if it is heated from minus 150 degrees Celsius to 25 degrees Celsius at 1 atmosphere? Answer: change from solid direct to gaseous state. What is the name of this process? Answer: sublimation. At atmospheric pressure, solid carbon dioxide sublimes and is known as dry ice. This is advantageous as it does not leave behind a residue of liquid as it performs its role as a potable refrigerant. Notice that the liquid vapor curve for carbon dioxide stops at a point just below a pressure of 10,000 kilopascals. This is called the critical point. Place the cursor on it and note the values of temperature and pressure. Answer: 31 degrees Celsius and 7,363 kilopascals. Now place the cursor at a pressure of 10 kilopascals and 40 degrees Celsius and click to see the particles. Move the cursor to a pressure of 1000 kilopascals at the same temperature and look at the particles again. What phase is carbon dioxide in on this part of the diagram? Answer: gas. How do the gas particles differ at the two pressures? Answer: they are closer together at the higher pressure. Put the cursor at a pressure of about 18,500 kilopascals and 50 degrees Celsius. Observe the particle arrangement carefully. In a liquid, the particles are touching and moving randomly. In a gas, they are normally far apart. However, at conditions of temperature and pressure beyond the critical point, the liquid and gas phases become indistinguishable and form one continuous phase known as fluid phase. Supercritical carbon dioxide, that is a fluid above 31 degrees Celsius and 7,363 kilopascal, is proving a useful unreactive solvent. It has replaced more harmful haloalkane solvents for extracting caffeine from coffee to make decaffeinated coffee. Phase diagrams are very useful for predicting what phase changes should occur in systems when temperature or pressure, or both, are changed. Set the cursor at minus 20 degrees Celsius and 100 kilopascals and track the diagram up to about 5,000 kilopascals. What happens to carbon dioxide gas at minus 20 degrees if the pressure is gradually increased? Answer: the gas is compressed until it liquefies. Set the cursor at minus 50 degrees Celsius and 100 kilopascals and track up to about 5,000 kilopascals. What happens to the gas now? Answer: the gas is compressed until it liquefies, and as the pressure is increased further, it solidifies. Set the cursor at 1000 kilopascals and minus 200 degrees Celsius and track across the diagram from left to right. What changes of state does carbon dioxide undergo? Answer: change from solid to liquid state followed by a change to the gaseous state. Summary: a phase diagram shows the relationship between the phases in a system as a function of temperature and pressure. Points on each curve on the diagram give the conditions under which two phases are in equilibrium. Areas between two curves correspond to conditions under which only one phase exists. The point at which the solid-liquid, liquid-vapor, solid-vapor curves intersect is called the triple point. This is the only set of conditions at which all three phases can be at equilibrium in a closed system. The temperature and pressure above which the liquid and vapor become indistinguishable is called the critical point. Under these conditions, the substance is called a supercritical fluid. On the phase diagram for water, the solid-liquid line has a negative slope. This means that the melting point of ice or the freezing point of water decreases with increasing pressure.